Okay, so I think we are meeting after a long time, right? You might have forgot everything. What we were doing, we were looking at elliptic curve crypto system, and I gave you in the last class examples of two examples actually of elliptic curves and how to find their points and so on. I just recapturing. So equation of the form y square is equal to xu plus ax plus b is known as elliptic curve because the genus of this curve is 1. Okay. So genus is a measure of smoothness. So that means you cannot find parameterization. You cannot do parameterization of this equation. I mean, if you want to understand in a loose term. And this quantity 4aq plus 27b square is known as discriminant. Okay. And so depending upon whether AB, you can take AB over real or complex. So you will get a, real or complex elliptic curve. Or you can take integer modulo P, which we have done. Okay. And also you can take it's as a finite field over any finite field, or also you can take it over a finite ring. More simplest term, it could be integer modulo n, Zn, okay? So we talked about some of these examples, I think last time. And there are certain additions. So what is the, I'm just recapturing what was the main thing. If you take, so basically, since we are considering these elliptic curves over finite structures, either finite field or finite rings and so on. So actually I can count how many points are there, right? And if you look at all these points, the collection of these points normally forms a group, okay, with certain conditions actually. And so that means if you take a point P on this elliptic curve, P is equal to x comma y, you can find another point, basically, so that means if you add P with another point Q, then P plus Q again belongs to the same set, right? Same collection of points. It will be another third point on the curve. So there is a way to define addition of 2 points, right? And why we look at elliptic curves? Because we can look at the discrete log problem in the sense of elliptic curve, that if you have a point P and repeatedly you add m times, you will get some other point Q. And since if m times P is equal to Q and P and Q are known, finding m is a difficult problem, right? So which is known as a discrete log over this structure. So now I'm going to summarize some of the properties of elliptic curve, and then we'll talk about one crypto system, Elgamal crypto system. So last time, this is what we have done. I think I gave you this as an exercise for you. If you look at, this field, then and if the equation is y square is equal to xu plus x plus 4, then you can find the points when it will be, elliptic curve. What are the points you can find actually, right? So you just vary the values of x and you can find the values of y. Okay. So, okay, that's all what we have done last time. So now I can look at properties of elliptic curve. Suppose E is an elliptic curve over FQ, filled with Q number of elements. Here Q is a prime power, or I will say M. Some prime power. Then the number of points, if I count the number of points on this curve, they lies between Q plus 1 plus 2 times root Q upper bound, and lower bound Q plus 1 minus 2 times root Q. This is a famous Haswell bound. The number of points upper bounded by this and lower bounded by this. So obviously, as you know, you can write down a computer program. In small cases, you can find the points, and there are different ways, there are different algorithms actually to do that. Okay, so So one main result which I would like to mention here, if E is an elliptic curve over FQ and Q is say P raised to power N for some prime N, for some prime P, then there exist integers N1 and N2 such that E plus is isomorphic to integer modulo N1 cross integer modulo N2. Okay. Further, N2 divides N1. So over FQ, if you look at elliptic curve over the FQ, then the collection of points is basically isomorphic to this Zn1 cross Zn2. Okay. This is one result. If number of points, is P or product of primes, then E must be cyclic. Cyclic group. These are some properties which one can prove actually. Okay, so now I think we can describe. So now you know what some of the basic stuff about elliptic curve. Depending upon what structure we are taking and these values of P, the kind of primes you use, there is a slight difference in you can have different kind of characterization of this group and okay, so I think even in the case of finite field or even finite ring, so there are interesting things altogether. And as I mentioned, over finite rings, not much work has been done. In fact, very recently there is a one paper which talks about the structure of this group, and we have also done some work in the classification actually of this curve. Anyway, so now I am going to describe Elgamal crypto system on elliptic curve. So essentially what we are going to do, we are taking 2 points P and Q on this elliptic curve E, and if you take point P and add it m times, you will get Q is equal to m into P. M is known as private key, right? So it is very difficult to determine. This is like a discrete log problem. Now actually a small observation that I am going to tell you, based on that, when we want to store these points on the computers, actually, there is something called, some observation. As long as, if you look at y square is equal to, ax cube plus bx, y square is equal to x cube plus ax plus b, if the right hand side is non-zero, actually you can find a way to simplify. You need to find one value of the pair. So a point P is equal to x comma y is a solution of the curve, right? You can just store one and you can find the other one. And that observation is easy. It saves our space for almost 50% in terms of when you want to store these points actually. So a non-empty or a non-infinity actually point on elliptic curve E is a pair x comma y, where y square is congruent to x cube plus ax plus b mod p. Now observe that given a value for x, there are two possible values of y. So if I choose one value of x, we are going to get two possible values of y, as long as this is non-zero. Okay. If it is zero, then obviously, that's not interesting case. As long as this is non-zero, for each value of x, we will have two values of y, right? and these values are negative of each other modulo p. Okay, since p is odd, you know, p is not equal to 2, p is odd, one of the value y is even, one of the value of y is even, and the other one is odd. So this you can also look at the data. When you calculate the data, you can actually observe these things. Therefore, we can determine a unique point p is equal to x comma y on E by specifying the value of x. Value of x together with single bit y mod 2. So this reduces the space by 50% or something, you know. So essentially what does that mean mathematically? We can have a function like point compress, you know, taking E to ZP cross Z2. So point compress function is something like this of P x comma y mod 2, where P is a point x comma y on E. Okay, so we are going to use this point compress function. Okay, so how do we find? So basically, this is a way. So we can take a point P on the elliptic curve and we can do the point compress. So I'll get this pair. Now, if this pair is given, how do we find the point? So essentially, there is a algorithm for it, which I am going to mention now. It is known as point decompress. Input is x comma I. So you just compute z. I mean, you compute xu plus ax plus b mod p. Okay. And if z is a quadratic non-residue mod p, then return failure. Obviously, in this case, you cannot do anything actually, right? Return failure. Else, what you do, just put this value here, mod p. If y is congruent to I mod 2, then return this pair x comma y. Okay. Else return x comma p minus y. This is our algorithm, right? Point decompress. Okay, so this is just an observation. So based on this observation, now I am going to describe this Elgamal crypto system, which is based on this elliptic curve. Let me describe that for you. Elliptic curve, Elgamal. E is a elliptic curve over ZP we are considering, and obviously P is greater than 3. P is not equal to 2. The P is a prime such that E contains a cyclic subgroup H, which is generated by P. P is a point of prime order. Okay, of prime order n, in which discrete log problem is infeasible. Okay, you will see later on, by choosing different choices or different values of P, certain algorithms like index calculus and so on, are not are difficult to find. I mean, to do anything for us. So now let H be a function from E to ZP, is a secure hash function. Okay, plain text is coming from ZP, and ciphertext we can say is coming from ZP cross Z2 cross ZP. Okay, and define our key space as E, P, M, Q, N, H, such that Q is equal to MP. Okay, so we have E, the elliptic curve, P, that point on the elliptic curve, right? M, then Q is another point. So we know that P is equal to M times, so Q is equal to M times P, and H is a secure hash function. So M is a basically some integer in Zn star. Okay. So once we have this setup, we can say that E, P, Q, N, and H are public key, and M is a private key. Okay, for small k is equal to E, P, M, Q, N, H, for a secret random number k. Zn star, and for a plain text x in ZP. This is your plain text. Encryption is ek of xk, point compress, ap x plus h kq mod p, and for a ciphertext y is equal to y1 comma y2. Y1 is in ZP cross Z2, and Y2 is in ZP. Decryption of Y is Y2 minus H of R mod P. R is equal to M times point decompress of Y1. So it's a bit technical thing here, but so I think I can just do one quick example for you. Suppose elliptic curve is y square is equal to x cube plus x plus 6 over z 11. Point P is equal to 2 comma 7. This is as the previous example. Bob's private key is M is equal to 7. Therefore, Q is nothing but 7 times P is equal to 7 comma 2. You can compute all these things. Okay. Suppose Alice want to send X is equal to 9. This is the secret that Alice want to send. Okay. She chooses a random value K. K is equal to 6. So KP is equal to 6 times 2 comma 7 is equal to 7 comma 9, and k times q is equal to 6 times 7 comma 2 is equal to 8 comma 3. Suppose this h function, I am assuming just for illustration, h of 8 comma 3 is equal to 4, then y1 is nothing but point compress 7 comma 9 is equal to 7 comma 1. You can actually compute all these things, and y2 is equal to 9 plus 4 mod 11 equal to 2. So ciphertext is y is equal to y1 comma y2. Okay, 7 comma 1 comma 2. So after receiving ciphertext, Bob used point decompress. 7 comma 1 is equal to 7 comma 9, and 7 times 7 comma 9 is equal to 8 comma 3, and h of 8 comma 3 is equal to 4, and 2 minus 4 mod 11 is equal to 9, which is your plain text. So I know normally these elliptic curve things are not covered in the first year many times, but that's all for. Yeah, one more thing I would like to mention here. There are certain cases now. Number one, if G is ZP star with multiplication, P is a prime, and alpha is a primitive element. So basically, the discrete log group that we study here, normally we have two pairs, G and alpha. Alpha is a primitive element mod P. So we take this group for discrete log. Second is, we have G is equal to F2n star, where alpha is a primitive element in F2n star. Primitive elements means order of alpha is whole group minus 1, right? If you remember. Third, when we take elliptic curve thing, E is a elliptic curve modulo a prime P. Alpha is an element in E with order of alpha is equal to Q, which is size of E divided by H. Normally we take H is equal to 1, 2 or 4. These are some special groups that have been used, So actually NIST in 2015, they have. So actually the first three cases, can be attacked using index calculus algorithm, so and so basically some of these things can be attacked using index calculus algorithm. If you remember that we talked about for discrete log problem, attack on the discrete log problem, and for some of the cases it is polarized flow algorithm. Okay, and I think the safest case for case 3 was P should be at least greater than 2 raised to power 224. Okay, so this was till to 2015, I think. So these values of primes that they choose, so they are safe against these algorithms. So as long as you increase the value of P, so you are safe here. By the way, one can talk about the security of Elgamal crypto system also, but I think that's all. I mean, we are not going to do too much. So one thing actually, so next we can cover signature schemes, and since you know few basics of elliptic curve crypto system, so maybe you can understand. So I'm not going into too many details about other algorithms as well. There are many interesting algorithms, but signature scheme I will show you how these are applied. After that, now, so that is probably another 1 or 2 lectures. After that, we still have enough time to cover either NTRU, if you want me to cover that, which is highly mathematical, or you want to take the easy route, like password. Should we talk about the password and so on and so forth? You know how they are created. That is entirely up to you. Which one you want? You want more mathematical stuff? Password thing? Okay, so because NTRU and all these code-based crypto systems require mathematical maturity, because those things are useful in post-quantum cryptography. Because you know, as you know that because of the quantum computers, RSA crypto systems will no longer be secure, and that's why, as I mentioned, the NIST has asked for the next generation of crypto systems beyond RSA. So there are two popular, basically code-based cryptography and then lattice-based cryptography. These are the two popular crypto systems which will provide security even if the quantum computers are there. They're even secure. Okay, so those are the modern things actually. You know, so sometime. So of course there is one chapter given. I think chapter 9 in your book it is given. So we can cover that. But I think in most of the applications, for example, if you look at you know, most of the modern applications, they talk about post-quantum crypto systems as well, right? Uh, Previous years, these things are not covered, but of course, it requires certain understanding about the coding theory as well, right? So when you talk about code-based cryptography, so other part is now the easy stuff like the protocol level things, you know, which we'll talk about, you know. So how? So I think if you know, like when you enter a password into the system, what happens? How salt is mixed there, and so on and so forth. You know, those kind of things we can talk about it. Okay. But I think signature scheme we will be covering in the next 2 lectures, and after that we'll talk. We have enough time to cover a few more things. Okay. I think that's all for today. I'm not going to do anything. By the way, should we take a quiz? No. So we need to take quiz sometime actually. Okay.